In the previous sets of videos, we had discussed about the shape of organic compounds. In this video, we are going to be talking about structural representation of organic compounds. A molecular formula will give us the information about the number of atoms, the different types of atoms in that particular molecule. So here in the structural formula, we will be representing all the atoms in that particular molecule. So to recap, you know, in Lewis structures, this is a single bond, this was a double bond, and this is a triple bond. So in the structural formula, we need not represent the lone pair of electrons on the hetero atoms. That is, in case of oxygen, nitrogen, we will not be representing the lone pair of electrons. So let's start. First is a molecule called ethane. I'm guessing you have a basic idea about nomenclature. So I'm using these names, and I think in 2-3 topics after now, we will be discussing the nomenclature of organic compounds. So first of all is ethane. So ethane's molecular formula is C2H6. So for the structural formula, we will represent all the atoms, which means this is ethane. So all the atoms are getting represented. In case of ethene, its molecular formula is C2H4. So C double bond, C ethene, right? So it has the double bond, an alkene. And then in case of ethyne, it will have a triple bond. So CH and a H. Okay, so in our structural formula, we are representing all the atoms in the molecule. So in case of methanol, methanol is CH3OH. Okay, so methanol's formula is, methanol structural formula is represented as this. So since I told you it's not mandatory for us to represent, I'm not putting the electrons or the lone pair of electrons on oxygen, or we can do that as well. It depends. Okay, for structural formula, it's not mandatory. Next, we are talking about condensed formula. So condensed formula is basically the structural formula, but it's a simplified version of the structural formula. So here, ethane will be represented as CH3CH3. Ethene will be represented as CH2, CH2, and ethyne will be represented as CH. So basically, again, methanol is CH3OH. Here we are not representing all the bonds, but we are concising them, we are condensing them, and we went from having such an open structure, which probably takes more time, and we're bringing it down to this. Also, another example, another thing that we do is, suppose let's take, for example, our molecule has the formula CH3, CH2, 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 and CH3. I mean, instead of writing 4 different carbon atoms and hydrogens, we can just write it as CH3, CH2, 1, 2, 3, and 4. So you have 4 carbon atoms in between, and we will just write it as a subscript and a CH3. Here also we have condensed the the molecular formula to give us this. So this is a condensed formula. I mean, imagine writing this particular structure over here. It is more time consuming, and that's why we have the condensed formula. But scientists decided, okay, this is again more time consuming compared to the bond line structure formula. So in the bond line structure formula, the carbon and hydrogen atoms are not shown. For example, let's take the structure, this one. Okay, so here you have 1, 2, 3, 4, 5, 6 carbon atoms. We know there are 6 carbon atoms in the structure. So what we will do is, we will use lines to represent this. So 1, 2, 3, 4, 5 and 6. Okay, again, compared to this seems much easier. Now the rules that you need to remember in this case are, first of all, the terminal carbons, they, unless and until mentioned, they are CH3. Okay. Secondly, here, these atoms, these carbon atoms, the number of hydrogens which are going to be attached to these carbon atoms is equal to the number of atoms it requires to maintain its tetravalency. For example, here this carbon atom is bound to 2 other carbon atoms, which means this atom will be bound to 2 hydrogens. This one also will be the same case. Here also it will be bound to 2 different hydrogen atoms. Again, let's take another example. Let's assume this carbon atom has another, it's bound to another carbon atom. Okay, so here also it will be a CH3. Now, do you think this will be a CH2 or a CH? So here, to make sure its tetravalency, or rather to maintain its valency is 4, let's first count 1, 2, 3. It's bound to 3 other atoms already, which means it only requires 1 atom and 1 atom of hydrogen for it to have the valency as 4. So basically what I'm trying to say is the carbons which are in between, they have the number of hydrogens is equal to whatever the number is that is required for the valency to become 4. And that's about it. So yeah, I mean, you have structural formula which represents all the bonds, all the atoms. Then you have a condensed formula which simplifies it, and if you have many CH2 groups in between, that is getting condensed to form and it's written as 4, or I mean the number is a subscript. And in case of a bond line structure formula, terminal carbons are going to be a CH3, and the ones in between will have the number of hydrogen atoms equal to whatever it requires for the valency of the carbon atom to become 4. Now let's look at like 2 other examples for this. Structural formula. Okay. Okay. So I'm just going, okay, structural formula, we're taking the example of 3-chloropentane. So 3-chloropentane is, structural formula will be, it has 5 carbon atoms. Okay, and at the third carbon, it will have a chlorine. So chlorine, and remaining will be hydrogens. So the condensed formula for this particular molecule will become CH3, CH2, CH, Cl, CH2, CH3. Now, to again change this, to help us get to the bond line structure formula, let me just write it like this: CH3, CH2, CH, CH2, CH3. Okay, so Cl. Now this can be written as, for the bond line structural formula, 1, 2, 3, 4, 5. 5 carbon atoms, and in the third position you have a Cl, and that's your bond line structural formula. The terminal carbon atoms are basically methyl groups, so CH3 and CH3, and the remaining carbon atoms will have the number of hydrogens to maintain the tetravalency. Another example is 3-methyloctane. Okay, I am not going to be writing the structural formula for 3-methyloctane, but we will be writing the condensed and the bond line formula. So 3-methyloctane, so octane generally has 8 carbon atoms. So CH3, 1, 2, The third carbon has the methyl group attached to it. 1, 2, 3, 4, 5, 6, 7, 8. So this can actually be condensed and written down as CH3, CH2, CH3, CH2, how many times? 1, 2, 3, 4, 4 times, CH3. So we're just condensing that further and writing it like this. Now the bond line structure formula. So there are 8 carbon atoms in this particular structure. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7 and 8. In the third carbon atom, you have a methyl group. And there you have the structure of 3-methyl octane. And let's face it, writing this is much easier than writing this or even the structural formula. I mean, imagine writing the structural formula for 3-methyl octane, quite complicated. Anyways, for cyclic compounds, the same rules are followed. So let's take, for example, you have propane, cyclopropane rather. Cyclopropane has 3 carbon atoms which are arranged in a cyclic form. 2, 3, 4, 2, 3, 4, and then you have a CH2. Now this is simplified and written as a triangle. Similarly, hexane. Two, 3, 4, right? So all these carbon atoms, so this is a cyclohexane. So when cyclohexane has to be written in a simpler form, we write it as this. We assume, again, in this case, you don't have anything called as terminal carbon atoms, but you have the ones in the line junction carbon atoms, and they will all have the number of hydrogen atoms will be equal to its valence, it's 4, I mean, it has to maintain the valency as 4. Similarly, cyclobutane, cyclopentane, and then you have chlorocyclohexane. So in this video, we had discussed about the various ways of representation of organic compounds. We went from structural formula, which represented all the atoms along with their bonds, to a condensed formula, which basically concised, and it made things a little easier. And we're not going to be representing each of these bonds, that is hydrogens and stuff. And also if there are various carbon atoms, which, like, if you have so many, and you can just mention the number as a subscript. And then we went to a bond line structure formula, which is even more simple, where we're representing it as lines. Okay, and terminal carbons are methyl groups unless and until written otherwise. So for example, here, so let's take this side, you have an alcohol group present, then we would just write it as OH. Okay, so unless and until mentioned otherwise, these are CH3s, and the carbon in the junctions are going to have the number of hydrogens equal to the valency as 4. Cyclic compounds, on the other hand, they are also represented in the form of the bond line structure formula. Instead of just writing the number of hydrogens in each of the carbons, we're just using the bond line structure formula to represent these atoms. In the next video, we will be talking about the 3-dimensional representation of organic compounds.